There we go. All right, thanks everyone for tuning in. Sorry for the delay. Today we're very happy to have a joint seminar by Matthew DeCross and Arjun Kar from the University of Pennsylvania, and they're going to tell us about their recent work on binding complexity and multi-party entanglement. So Matthew and Arjun, thank you very much, and the floor is yours.
All right, great. Thanks for inviting us. It's a pleasure to speak for you today. So as the title says, we're going to talk about a new kind of complexity called binding complexity, and its relation to multi-party entanglement, both in qubit systems and continuous systems. So to start off, I should tell you what this new kind of complexity is. Well, after I tell you who's on the project, so is these four people at Penn with us, Vijay Balasubramanian, Arjun is here, and Ankar Parikar, one of our postdocs. And this is related to work by a lot of previous people on multi-boundary wormholes, geometrizing complexity, Roe Jefferson and Rob Myers, among other people, on circuit complexity and quantum field theory, groups on tensor networks, and this last group at the bottom who worked on robustness measures for multi-party entanglement. So what is this new kind of complexity? This binding complexity will be a quantum circuit complexity, but it will only count gates that create entanglement between parties. It will not count, in particular, gates that act within a single party when a Hilbert space admits some factorization. So to understand why we might be interested in this kind of complexity, let's examine it first in some simple qubit states. So when you have a three-party factorization, it's well known that the two SLOCC equivalence classes of multi-party entanglement are the GHZ and W classes. We can consider the n-party generalizations of these states. So for example, the GHZ state, as shown at the top, this has a known explicit circuit construction that you can see on the slide. It involves a single qubit gate called a Hadamard gate, and a number of two qubit gates. In this diagram, they're C0 gates that actually will show an explicit form for later. And so this circuit will create the GHZ state from n factorized zero reference states. And there are two comments to make about this state. The first is that this circuit uses the minimal number of two-party gates possible. And the reason for that is that it uses O of n entangling gates. In this diagram, it'll actually use n-1 entangling gates. And any fewer than that, then a number that scales with n won't actually be able to entangle all the qubits together. So you won't end up with a state that's entangled on all n qubits. So this circuit actually uses the minimal number of entangling gates. The other comment is that the entanglement entropy, which of course is the von Neumann entropy of, in this case, one party with the rest, the reduced state on one party. The entanglement entropy of a single party, S1, is quite large, even as n grows large. It's log 2, it's a constant. And so you might interpret that as saying that the entanglement is very strong in GHZ states. In this talk, we're going to take a different kind of view of what strong entanglement means and say that actually the GHZ states have very fragile entanglement, and that this large entanglement entropy means that removing one qubit actually removes almost all the entanglement. So we're going to want to use the binding complexity to diagnose how robust or fragile entanglement is in that sense. So let's look at the other class of states, the W class, again generalized to n parties. Unlike the GHZ state, there isn't a known minimal circuit construction. There are known circuit constructions. For example, one was provided by Dijker in this reference. And they require order n squared entangling gates. And correspondingly, the multi-party entanglement structure in W states is much more robust. For example, the state is not separable when you trace out any number of parties. And also correspondingly, the single party entanglement entropy goes to 0 as the number of qubits grows large. And again, you should imagine that as saying that as any number of parties is traced out, you remove very little entanglement. The entanglement remains is very robust. So binding complexity, this complexity that counts entangling gates, should diagnose robustness of entanglement in the sense that the entanglement is widely distributed among the parties, and it's also difficult to destroy by removing some of the parties. So let's talk also a little bit about what we should expect this kind of quantity to correspond to an ADS CFT. As we know, for the normal complexity, we have these volume and action conjectures by Susskind and collaborators in a series of papers. And they hypothesized that maybe the complexity of the boundary state dual to a wormhole geometry corresponded to the volume of the wormhole. Specifically on this Penrose diagram, it would be the volume of the maximal Cauchy slice in the bulk anchored at 2 boundary times. That's this blue line in the diagram. So you might imagine that if we only count the gates that entangled the 2 parties, then it should involve some kind of shared region. So you might imagine that it corresponds to the volume of, say, the wormhole interior, if you believe the complexity equals volume conjecture. Or maybe there's some corresponding action quantity. It turns out this is not going to quite be satisfactory for one reason among many is that the binding complexity is going to be invariant under the boundary time evolution because this doesn't actually create entanglement between the 2 CFTs. A different proposal you might think is true is that the binding complexity is identified with the interior volume of some Cauchy slice with minimal interior volume, like the red slice. When your wormhole has 2 boundaries, this actually appears to be 0. If you stretch the horizons, you'll get a contribution proportional to the entropy of those horizons. But you can generalize this to wormholes of higher number of boundaries, and we'll do that later in the talk. And this is rather speculative, but with this proposal, we're going to be able to get, say, a scaling relation between complexity and entropy that will compare to some field theory calculations later. So let me briefly outline the results and what we'll discuss for the remainder of the talk. So first, I'm going to use this binding complexity to establish some bounds relating it to multi-party entanglement in qubit systems to show that really this does diagnose something about the multi-party entanglement structure and not just, say, the entanglement entropy. Moving on to infinite dimensional Hilbert spaces, we'll use the Nielsen's formalism of geometrizing complexity to compute the binding complexity in Gaussian states. So here there'll really be 2 novel things. First is that we're going to compute, again, the binding complexity, not the ordinary complexity. And we're going to relate it to the multi-party entanglement structure in these states. The other thing is that we're going to demonstrate a new formalism for computing complexity. It takes advantage of the group structure of the unitary preparing states. And so we'll actually be able to basically reduce the geodesic equation to a first order equation that is much easier to solve. So in ADS CFT, the natural setting for studying multi-party entanglement and complexity will be multi-boundary wormholes. So we'll discuss their construction a bit and some expectations for the binding complexity, say with intuition from tensor networks. And also using our intuitions from multi-boundary wormholes, we'll try to construct Gaussian states mimicking the procedure in ADS CFT of constructing the boundary state with Euclidean path integrals on the bulk. So we'll consider a kind of dimensional reduction of the bulk geometry and do the Euclidean path integral on a graph that will prepare these Gaussian states. And lastly, if we have time, we'll talk about coherent states and the creation of complexity by adding a deformation to the Hamiltonian. And this will follow some of the wormhole story from Maldacena and Chi of introducing a deformation that enlarges a wormhole or creates a wormhole. Good, so let's start with bounds in qubit systems. So again, the goal is to relate the binding complexity to entanglement measures in a finite Hilbert space. Let's suppose at first for simplicity that we factorize into 2 parties. In the circuit, A will be the red party and B will be the blue party. And we have some target state that's prepared from, say, a factorized reference state with a sequence of unitaries. In this circuit, we have 7 unitaries. And NAB will be the number of gates acting across the partition. So in this circuit, we see that U3, U5, and U6 act across the partition. And let me remind you that the binding complexity is the number of gates acting across the partition in the best possible circuit. So we're going to want to minimize NAB, the number of gates acting across the partition. And the key idea we're going to need to relate the binding complexity to entanglement measures in these states will be the operator Schmidt decomposition. So like states, operators emit a kind of factorization between parties, as shown here. You can split an operator across the partition. And there'll be some number of terms for any given operator. The number of terms will be called the operator Schmidt rank. As an example, we see the C0 gate here. The C0 gate has two terms. The C0, of course, is a controlled bit flip. So if the first bit is 0, then the second bit is not flipped. So the first bit is 1, the second bit is flipped. And so there are two terms in the decomposition of the C0 gate, so j equals 2. In general, we might have many gates that appear in a circuit, and we'll call j sub g the maximum operator Schmidt rank of any of the gates that appear in the circuit. Good, so with that notation established, let's first state the results, and we'll prove one case of them for the sake of time. The first case is, suppose you can split your qubit system into n parties. So now the binding complexity computes all gates acting between any two different parties. Then the binding complexity is bounded below by all of the sum of all of the single party entanglement entropies times a constant, which is in terms of the maximum operator Schmidt rank. If we have a three-party factorization, we can go beyond just entanglement entropy and say that the binding complexity is bounded below by this quantity E, which is related to the negative eigenvalues of the partial transpose of rho BC. And you might recognize that this quantity is related to the entanglement negativity, which is a known diagnostic of separability. In fact, we can write this bound in terms of the negativity. It just doesn't look quite so nice. So really, the binding complexity is related to the multi-party entanglement structure in these states. It says something about the separability on tracing out some of the parties. Good, so let's see how the techniques we use to prove one of these bounds. So suppose again, we're in the case that our Hilbert space emits a bipartition, and consider all the gates that act across the bipartition. Here we've shown the same circuit diagram as before, and on all three gates that cross the partition, we've employed the operator Schmidt decomposition to cut the gates. So the resulting state that we prepare will be written in terms of its Schmidt decomposition, but in particular, its rank is bounded above, using the fact that all the unitaries that we've cut have operator Schmidt rank, which is bounded above by the one of maximum operator Schmidt rank. Since we have NAB such gates that we've cut, the rank of the reduced density matrix on one of the parties is going to be bounded above by, well, j sub g to the number of gates acting across the partition, NAB. Good. But if that fact is true, then it's pretty easy to see, say, by comparing to the maximally mixed state, that the von Neumann entropy of A as compared to B, of the reduced state on A, is bounded above, basically by taking logs, by the number of entangling gates, again, times a constant related to j sub g, the maximum operator Schmidt rank. Now comes the key fact that the circuit we used to prepare our final state was not necessarily the optimal circuit. We didn't necessarily use the minimal number of entangling gates. So NAB is not as small as it could be. We don't have the tightest upper bound possible. But we could have used the optimal circuit, and in that case, the right-hand side would be minimized. We would use the smallest number of entangling gates, as that's the definition of the binding complexity. So in that case, we see that we obtain a relation between the binding complexity and the single-party entanglement entropy for the bipartition. So these cutting arguments generalize basically to prove all the other inequalities.
Well, sorry, I have a question.
Yes.
So just I may have missed the definition. So in the binding complexity, you're just counting the gates that act across the bipartition, right? So you're not weighting the gates by their Schmidt. Right?
No, we're not weighting at all. They're all of equal weight as long as they entangle.
So an operator which has a, yeah, okay. You're counting, so the Schmidt rank is somehow kind of related to the entangling power of the gates, but you're not taking them into consideration.
Right. So the higher the Schmidt rank of of a particular gate, you might think the more entanglement it creates.
Right.
Good. Right, so these arguments work quite generally to prove both the inequalities in terms of the negativity and the entanglement entropy.
I have a question about I have an online question. Can you hear me?
Yes.
Okay, super. So can you go to the picture where you're depicting these 7 unitaries? So I'm confused about actually A1, A2, A3. Like, you mean like these guys actually are connected, or is not like one gate acting on the left and the other one acting on the right? Because like this does not change entanglement, right?
This is, I think, just an indicator for this index that appears in the
Okay.
decomposition. Yeah.
And sorry, what's the definition of J sub G and NAB?
So NAB will be the number of entangling gates in the circuit.
Right.
J sub G is the maximum operator Schmidt rank of any gate that we've used. So it's the one that entangles the most in some sense.
Right, but wouldn't you say that a tighter bound is simply the product of the A's?
So the A's are not single numbers. The A is this index that's looped.
No, but
So it runs up to J.
Yeah. No,
Oh, I see. You might say the product of all the individual J's. True, but you don't necessarily know, say, what gates comprise your circuit a priori.
oh, okay.
Yeah, at least in the optimal circuit. Good, so let's go on now to talk about the binding complexity in these Gaussian states, moving to infinite dimensional Hilbert spaces. And the key idea here, as used by Nielsen and by Jefferson and Myers and by many others now, is to geometrize the problem and to compute the complexity of a particular unitary operator as a distance in some Riemannian manifold. So to do this, we're going to want a metric on the group of unitary operators. And in particular, because we're interested in computing binding complexity, as opposed to any other kind of complexity, this metric needs to assign zero distance to directions that correspond to single party operators. And again, we're going to weight all of the entangling operators the same. So let's run through some math preliminaries. So we're going to have some set of operators in the Lie algebra, and we prepare our unitary gates by path-ordered integration of these operators. The VI here are some set of velocities. I'll show a figure on the next slide that might make this clear. So we'll define a metric on the Lie algebra in terms of the Cartan killing form. Without any constants in front of that, this would be this would extend to a bi-invariant metric on the group of unitaries. But we need to weight different directions differently in order to weight the entangling gates and not the single party gates. So we'll include some cost factors in this metric that have been written like this to make it symmetric. And we'll tell you explicitly in a few slides what these cost factors ought to be. So here's the geometric setup. The idea is there's some unitary U we want to prepare, and we're going to prepare it by some path in the manifold of unitaries. And VI is the instantaneous velocity along this path. Good. So with these cost factors, the metric on the Lie algebra extends to a right invariant metric on the space of unitaries. This metric would be bi-invariant if not for the cost factors. And it turns out that for manifolds with this group structure, the geodesic equation takes a particularly nice form that you might recognize in the first equation here. It looks a lot like the Euler equation for rigid body motion. You might call it the Euler-Arnold equation. And in the second line, we've written it in terms of indices and the structure constants. So here V and L are operator versions of the velocities along the path. And I is this matrix defined in terms of the metric and the Cartan killing form. So this is just the geodesic equation, but it's the geodesic equation for the velocities. And this is going to make the problem a lot simpler since that's what we actually want to obtain in the end to compute the complexity, as we'll see. Before, with the qubit systems, we were interested in the complexity of states as opposed to just unitary operators, which we've been discussing now in the context of geometry. So to find the state complexity, the procedure is to find the minimal complexity unitary that creates that state from a particular reference state. And so the general procedure that can be iterated here is to first solve the Euler-Arnold equation to find the form of all the velocities, and then to implement boundary conditions on U by forcing it to prepare the state of interest, the target state, to actually fix the value of these velocities. Good. So again, we have these cost factors that we need to address. So the metric, recall, was given in terms of the Cartan-Killing form times some constants that we called cost factors. And these were required in order to weight certain gates as being entangling so that we can compute the binding complexity, and so that we can discount gates that are not entangling. And so we choose these cost factors correspondingly. All gates that act on multiple tensor factors will have the same weight, that's just 1. And gates that don't have a very, very small cost factor that we've written as epsilon squared, simply to make the metric invertible, it can be treated as 0 for all purposes, and we'll take it to 0 at the end. And so, end of the day, the binding complexity will be the geodesic distance for the unitary that creates the state of interest, with the caveat that the metric that appears in this geodesic distance has these cost factors that only count directions that entangle. Good. So now let's state the model we're working in. This is, again, the model originally used by Bro Jefferson and Rob Myers about a year and a half ago now, which is working in this class of Gaussian wave functions for a set of oscillators, for example, from the lattice quantization of a scalar field. So our target state will be some very general Gaussian state, and our reference state will be factorized in position space. It won't have entanglement between the oscillators. Our gate set will be chosen in terms of these phi's and pi's, the essentially position and momentum operators. This is a minimal gate set, essentially, to create entanglement between the oscillators. So the final state wave function will take to have a very special form that we'll refer to a few times, especially in Arjun's half the talk, which we call omega f. It'll have this block form. And the reason is because we're interested in using the binding complexity to study the multi-party entanglement structure. So we partition the oscillators into m parties, and there'll be n oscillators in each party. So for example, this omega matrix, remember this is the matrix that appears in the exponential of the target state. This omega matrix will take this block form, where oscillators will couple to oscillators in other parties with the same strength lambda 2. All oscillators to all oscillators in all other parties couple with that strength. Within each party is within this omega lambda 1 block, so the self-coupling will be omega, and oscillators will couple to oscillators within their party with the parameter lambda 1. So all oscillators will be treated completely equally, and will couple to all other oscillators with these different strengths. And remember, again, the operators we're interested in considering for computing the binding entanglement will be the ones that create, will be the ones that entangle oscillators that are in different parties. So ij of Oij need to be in different groupings of these oscillators. So once we've specified that final and initial state, we can go ahead and solve the Euler-Arnold equation and fix boundary conditions. And actually, the solution ends up being very simple. You should look at our paper for further details. But in many cases, the simplest cases, these velocities can be fixed to be constant. And one finds a very simple form for the binding complexity in terms of the number of parties, m, and 2 particular eigenvalues of that matrix omega that I showed you on the previous slide. The eigenvalues are below. They're given in terms of the couplings. One particularly interesting note about this formula for the binding complexity in the Gaussian states is that it's finite as the number of lattice sites n goes to infinity. Now, this property is not true of other types of complexity, which naively diverge as the lattice quantization is lifted. So let's use the binding complexity to examine the entanglement structure in these Gaussian states. A remarkable fact is that the binding complexity and the entanglement entropy are actually both controlled by the same parameter. And that lets us express the complexity in terms of the entropy in this very simple linear relationship with these two coefficients, alpha and gamma. We see that gamma will be a particular term of interest. Gamma scales as log m, at least asymptotically. At the below, you see the plot that the corrections are indeed quite small unless the entropy is small. The linear approximation is very good. Good. So the complexity is given in terms of the entropy, and that tells us something about the entanglement structure of the state, that indeed the binding complexity is somehow counting entanglement, which should really have been obvious. But as we showed with the qubit states, the single party entanglement entropy can be a misleading characterization of the robustness of entanglement in states. When we have just one oscillator in each grouping, n equals 1, we can explicitly check how far the state is from separability, as measured by the so-called Gaussian negativity, which was proposed by Simon in this paper, although not under that name. And this is derived from the Paris-Horodecky partial transpose criterion for separability. And computing the Gaussian negativity that Simon provides us, we find that actually it's controlled by this same parameter that fixes the binding complexity and the entanglement entropy. And so the binding complexity has, again, a linear relationship in the log of the Gaussian negativity with now rational corrections, and the particular constants change. So, okay, the binding complexity is given in terms of some kind of multi-party entanglement measure. You might worry that because all these quantities are controlled by one fixed parameter, that maybe they're all just increasing because the entanglement entropy is increasing. And it's not really, these things are all correlated somehow, but maybe it's not a property of the multi-party entanglement. But in fact, we can show by varying the various parameters we have in the problem that even if we fix the entropy of the final state, the binding complexity will increase as the negativity increases. Which really shows that there is some correlation here between the binding complexity and the real robustness of the multi-party entanglement structure. Good, so now I'll pass you over to Arjun, who will start off talking to you about some of the applications and analogies of this idea to holography. Any questions on the first half before I go?
I do have a question online. So my question is, what kind of multipartite entanglement can you have in Gaussian states? In the sense that Gaussian states have very simple pattern of correlations. I mean, they just have non-trivial two-point correlations, nothing else. I know that entanglement is not really a correlation, but I mean, it's a bit confusing.
Sure. So I think I'll partly defer that question to Arjun's section on Euclidean path integrals, because we're going to show a procedure for constructing some very different kinds of entanglement structure in the Gaussian states using that procedure. And you can really explicitly see in that procedure how the entanglement structures are different. So let me defer that for Arjun.
All right, thanks.
Just one comment on that question. So the differences that we're going to see in different classes of Gaussian states will appear in these constant coefficients of the binding complexity that Matt was telling you about. These alphas and gammas will have different scalings in particular when we consider different classes of states. And so the goal will be to find a class of states that reflects the holographic scaling, actually. So let me tell you a little bit about the gravity side of things. So you've heard about binding complexity in qubit systems, and we've also covered the Gaussian state Nielsen binding complexity using the Euler-Arnold approach. And we have a proposal for what this binding complexity is supposed to be computing in the bulk side of things. So we're proposing that it's going to be equal to the interior volume of some multi-boundary wormhole states. So let me just briefly remind you how this construction goes. So multi-boundary wormholes are some natural classes of entangled states in ADS-CFT, and they're particularly nice because the entire geometry is actually controlled by the time reflection symmetric slice, which is just the holographic disk H2 quotiented by gamma where gamma is some discrete subgroup of the isometry group. So here you can see a picture of the hyperbolic disk. And what is the action of gamma? Well, gamma effectively specifies some pairs of geodesics on the hyperbolic disk. So you can see we've drawn 2 geodesics in blue and 2 geodesics in red in the picture. And this quotienting action of gamma is going to identify these geodesics on the disk pairwise. So the blue geodesics will glue themselves together and the red geodesics will glue together. And you can kind of imagine what's going to happen to this surface as this identification is made. If you look at the region B3 on the boundary of the disk, after the blue geodesics are glued together, the endpoints of B3 will be glued and B3 will become topologically a circle. And the same thing will happen for region B2 after the red geodesics are glued together. And finally, B1 and B1 prime will have their endpoints glued together to form a final boundary region. So this picture is showing what's topologically a 3-boundary wormhole. And the dual CFTs are supposed to live on these boundary circles. That's an equal time slice of the dual CFT. We've also denoted by H1, H1 prime, H2, and H3 the causal horizons of each one of these boundaries. So if you were to go into the CFT and compute the reduced density matrix on a single boundary, and then use that to compute the entanglement entropy, what you would find by the Ryutakanagi formula is exactly this length H3. There are some subtleties with that statement that are dealt with in the paper, but we're going to take these H3, H2, and H1 prime and H1 to be the Ryutakanagi surfaces for each boundary. So if you're not familiar with tensor networks, don't worry so much about this next part of the talk. This is just some intuition for what we expect for the binding complexity. So we have these wormholes. So now we'd like to understand how exactly we can compute the CFT complexity from them. So suppose we have a holographic tensor network that is preparing the boundary state, which is dual to this geometry. And these types of networks were studied by these 2 individuals, Peach and Ross, in this paper. And these networks are essentially constructed by just taking a tensor network on the hyperbolic disk and then superimposing this quotienting subgroup gamma on top of that. And the network will respect the geodesic identifications. So if an edge is, say, falling into the red geodesic, it will emerge from the identified red geodesic on the other side. So in the original discussions of holographic tensor networks, there was a procedure that they defined called entanglement distillation, which involved acting by local unitaries on each boundary to step-by-step disentangle the tensor network. So to disentangle some tensors from the network. The actual details of this procedure are not so important for us, but the upshot is that given a tensor network, say in a multi-boundary wormhole geometry, you can run this entanglement distillation procedure, and the output is a much simpler network where a bunch of tensors in the network have been completely disconnected. So that's these open circles outside the causal horizons. And then there are some leftover tensors that live just outside the causal horizons that have legs falling into the interior of the wormhole. And then behind all the causal horizons, there's the rest of the network. So that's this large tensor in the middle I that we've denoted here. So what this means is that the tensors that act on multiple boundaries live in the interior region or along the causal horizons. So if we want to compute the binding complexity as the, say, tensors that act across multiple boundaries rather than on a single boundary, what we should do is we should count up the tensors along each horizon, and we should count all the tensors in the interior of the wormhole. So if we imagine that each tensor is occupying some constant fraction of area in the geometry, then the interior volume plus the stretched horizons, where we've moved the causal horizons a little bit away in order to capture the tensors that have legs falling into them, falling into the interior, then this volume plus the stretched horizons should count the number of tensors in the distilled network. So that's our expectation. For binding complexity, we expect that there will be a term proportional to the entropy by the Ryutakanagi formula. We've exchanged the length of the horizon for the entropy S of the ith horizon. And there should be a constant term gamma that we say should correspond to the interior volume of the wormhole. And we should note that this is a similar scaling to complexity of formation. And we can actually compute the interior volume exactly using the Gauss-Bonnet theorem. It's a simple calculation of a constant curvature Riemann surface with some boundaries. And the Gauss-Bonnet theorem tells us that there is one term that goes like the length of each causal horizon. So we've used the Ryu-Takanagi formula to exchange those lengths for the entropies. And there is a term that is the topological piece proportional to the Euler characteristic. That's this 2 pi times m minus 2 term. And we say that that term should be the interior volume contribution to the binding complexity. So any questions about the expectations for the binding complexity from the holographic side? All right. So now that we have some understanding of...
I do have a question online. Was it important that the tensor network is made from perfect tensors, or like?
No, it's not at all. So the shape, I think in this paper by Peach and Ross, they study various types of tensor networks. I'm not quite sure what they are using, but it's not so important for any of our arguments that the tensors themselves have any particular structure. No.
Okay, thanks.
Yep. All right. So now that we understand the bulk expectations, let's talk a little bit about some states in our oscillator system that we want to see. We want to compute the complexity and see if they correspond to the holographic scaling. And again, just to be clear, by holographic scaling, I'm talking about those parameters alpha and gamma and how they scale with the parameters of the wormhole, say the number of boundaries. So far, we've restricted our attention entirely to these Gaussian target states of this form that are defined by this matrix omega. And they have a very special structure, this omega f that Matt was telling you about, which are symmetric among all the boundaries, and they're symmetric within a given boundary. So there are only actually 3 free parameters associated with this omega f. There's the self-coupling omega, little omega, I mean. There's the internal boundary coupling lambda 1, and there's the cross-boundary coupling lambda 2. So there's actually no obvious connection to holography of these states, and the oscillator system we have is definitely not holographic, at least not at finite n. So unfortunately, we cannot compute binding complexity for a truly holographic system, although it would be very interesting to do so. We'll try to get a little bit closer to states that we want by mimicking the construction procedure from ADS3 CFT2. So the original holographic multiboundary wormholes were constructed in ADS3, and they had a particular procedure to construct those. And as you might have guessed from the title of this section, they used Euclidean path integrals. So let me just remind you how that story goes. In ADS3 CFT2, the boundary CFT state, which is dual to a time reversal symmetric slice topology sigma for your wormhole, is created by performing the Euclidean path integral of the CFT over this topology sigma. So, of course, if I perform the Euclidean path integral and I leave the boundary conditions of my fields open on the boundaries, I'm creating a state which lives in the tensor product Hilbert space, which is precisely what I want for a multiboundary wormhole. Now, this construction is in 3 dimensions, but we only have a quantum mechanical system that we're working with, so we need some way to make contact with that. So let's imagine that we start with a Riemann surface, say this pair of pants here, and we want to understand how to construct a state that is morally like this state, except in 1 dimension. So any Riemann surface that is of this form locally has a circle factor, and that will be very important because that means that there's a consistent notion of dimensionally reducing these Riemann surfaces into 1-dimensional manifolds with singular branching points. So you just do the very obvious thing. You take the local circle everywhere and you shrink it down to a point. And what you're left with from the pair of pants is this singular trivalent vertex object. So we'll call these things graphs. And their only degrees of freedom are their vertices and the length of the edges. So as you might have guessed, we're going to consider our harmonic oscillator path integrals on exactly these graphs, which are dimensional reductions of these Riemann surfaces that create the wormhole in 3 dimensions. So for each edge, we'll label the vertices by, say, x and y, and each edge will have a weight called beta, and beta is how long we're going to perform the Euclidean path integral for. So that's given by the harmonic oscillator propagator in this expression here. And the result of this path integral is exactly the Miller kernel. So you can evaluate this just by inserting complete sets of energy eigenstates and performing the sum explicitly. And the important thing about this function k, x, y, beta is that it is precisely a Gaussian in the variables x and y. So that will be very important for our analysis. Because the path integral on a graph G can then be performed by splitting the vertex set into external and internal vertex sets. So let's call the external vertices x vector and internal vertices y vector. Then the wave function corresponding to any particular graph that has some external and internal vertices is obtained just by integrating the product of all the Miller kernels for each edge in the graph over the internal vertices. So for each edge, we get a factor of this k function, and we want to integrate over the internal vertices. So all of these integrals are actually Gaussian, and we started with a Gaussian, so the result of these integrals is also Gaussian, with some irrelevant normalization that we're not concerned about. But the point is that these path integrals on these graphs can be used to generate various Gaussian states for us that have some, that are defined by some matrix omega. So if we just start doing the path integral on an arbitrary graph, the form of the wave function will be quite complicated. So this omega matrix may not have a lot of structure. It will have many, many degrees of freedom, many different couplings associated with it. So we need a little bit more control over the situation. So we're going to consider graphs with a very restricted topology and edge length. And we're going to say that they need to be symmetric both within a boundary and between all boundaries. So you can see a picture here of what is essentially the dimensional reduction of a 3-boundary wormhole. So there are 3 different parties that we're considering here. And the internal lines, so lines between, say, y1 and yc, or y3 and yc, those all have weight beta 2. And the external lines, which are between, say, any x vertex and any y vertex, those external lines all have weight beta 1. So if you perform the Euclidean path integral for the harmonic oscillator on such a graph, what you will obtain is a wave function of exactly the form omega f that we discussed before in the previous part of the talk. But the couplings omega lambda 1 and lambda 2 are now dependent on the graph moduli, beta 1 and beta 2. So we can study the dependence of the complexity on these graph moduli as we vary them. So again, the complexity can be computed using the same techniques, and the dependence on the moduli is shown below. So there are 2 things to note about this graph. First, in the large beta limit, which is morely like the low temperature limit, the boundaries are becoming spatially decoupled. At least that's the wormhole picture of things, and the complexity vanishes. So this is like the very small entropy regime. In the small beta limit, which is the high temperature regime, this is where all the boundaries are becoming very, very close to each other. And this is the regime of very large entropy, and the complexity is suitably large at that point. So unfortunately, the complexity scaling of states like omega f that we discussed does not quite match holographic expectations from the wormhole interior. So if you've been paying attention very carefully, you probably already observed this. The topological piece of the volume, which is proportional to the Euler characteristic, scales linearly with the number of boundaries. So remember, here's the Euler characteristic, and we always consider genus G equals 0. But fully symmetric states have a binding complexity where the constant piece, the piece that is independent of the entropies, scales like the logarithm of m. So this is a pretty large separation. So unfortunately, our dimensional reduction procedure didn't quite give us the states that we wanted. There are 2 possible explanations for this, I suppose. The first is that this dimensional reduction is a little bit ill-defined, and the second is that these harmonic oscillators are not holographic at all, so we shouldn't really expect to do very well with them. But we can still try and construct a state which resembles the holographic scaling more closely. So we can try and do a little bit better. So that's where this family of graphs we call bipartite entanglement graphs enters. So there's no sense in which, at least it's not obvious to me that there's a sense in which this graph is a dimensional reduction of another one, but it does give us an interesting scaling of complexity with entropy. So take a look at the form of this graph. What's pictured is essentially a 4-boundary wormhole, a genus 0 4-boundary wormhole. And you can see that on each boundary, there are subgroups of oscillators that are partitioned, and each subgroup is connected to only one other boundary. But on each boundary, there exists an oscillator that goes to all boundaries, or there exists at least one oscillator that is connected to any other given boundary. So this path integral, the result of the state that we get by doing the path integral on this graph, will not be of the form omega f. It will not be a fully symmetric state that we were considering before, but nevertheless, these states are still exactly solvable in the sense that we can compute entanglement and complexity, because the path integral factorizes across the separate branches. Despite the fact that the path integral factorizes, which usually means that some entropy is going to vanish, the division of the oscillators into boundaries is crossing the factorization, and that point is crucial. The fact that the division crosses the factorization means that there is still non-trivial entanglement and non-trivial complexity between the boundaries, while preserving the fact that the graph is fully solvable. So let's call a single component of the bipartite entanglement graph a branch. So we've pictured a branch here, and the branch has a fixed size, which is determined by the number of oscillators on each boundary divided by the number of the rest of the boundaries. And the entanglement entropy associated with any one boundary is proportional to the entanglement entropy associated with this branch graph by a factor of m-1. So this is pretty reminiscent of the Ryu-Takenagi formula, because in this scenario, the entropy is proportional to the number of edges in a minimal cut. So let me remind you how that goes. If we consider boundary number 1, clearly a minimal cut that separates boundary 1 completely from all other boundaries is proportional to 3, because there are 3 edges leaving boundary 1 to the rest of the graph. So this is precisely the idea of the Ryu-Takenagi formula in certain constructions. So that's quite interesting. And the complexity for these states is there's a piece proportional to the one boundary entropy, and then there is a constant piece, which is square root of m times m-1. So we didn't quite get an asymptotic scaling of the constant piece to be linear, but at least in the limit of a large number of boundaries, the topological piece of the volume is now matched by these sorts of states. Any questions about Euclidean path integrals before I talk about the coherent states in perturbation theory?
So one property was that the complexity vanishes for beta to infinity, so for the ground state.
Uh-huh. Yeah, so beta to infinity is morally like the limit where the boundaries are becoming very separated. So if you think in the ADS3 CFT2 case, what's happening is the wormhole is becoming very small and narrow as the boundaries are sent off to infinite distance from each other. So what's happening in that case is the Ryu-Takenagi surfaces are basically pinching off, and there's no entanglement between any of the parties. So that's the intuition for why even the binding complexity should vanish in that case. Mm-hmm. Yep. All right. So let's talk about one final test of our conjecture about binding complexity and the interior wormhole volume. So we can use this Nielsen formalism to test our conjecture with the results of Maldacena and Chi in this work. And they showed that a wormhole can form in the ground state of a deformed theory. So let me explain what I mean by that. So we'll start by considering the complexity of a coherent state. So this state psi is a coherent state on top of some base state, psi 0. And we are creating it by the exponential of some operator. And recall that the unitary is given by this expression, which Matt showed you before. And again, these velocities obey the Euler-Arnold equation. And the boundary condition of the geodesic equation is just this exact unitary that we would like to create. So we can take the limit of small t. So remember, t was this coupling of this operator creating the coherent state. And we can expand the velocity in powers of t. So then there's a long calculation you have to do to solve the Euler-Arnold equation order by order in t. But the upshot is that the complexity is proportional to t. So the second order contribution of the complexity actually vanishes, and we're left with a complexity which is linear in t. And the constant of proportionality is the norm of this operator with respect to the complexity metric. So what that means is you take the coefficients of this operator that are that correspond to terms in the operator that are crossing boundaries, and you only count those terms in calculating this norm. So we can now run this general story for our oscillator system with the so-called single trace deformation in the style of Chi and Maldacena, and the new vacuum of the oscillator system with this H interaction is a coherent state on top of the old vacuum. So remember that the original vacuum of the oscillator system is entirely decoupled, but we've introduced some interaction now, so the ground state has changed. And it has changed in particular by this B matrix. So just using the result that we just quoted, the binding complexity at first order in G, the coupling, is just proportional to the operator norm of this B matrix with the given complexity metric. So we can see that the binding complexity is now positive, whereas in the original vacuum, the binding complexity vanished exactly. So adding a single trace deformation to the Hamiltonian in the style of Chi and Maldacena can change the vacuum to a state with higher binding complexity, which is exactly in line with the holographic results. So in summary, we've introduced a new quantity called the binding complexity, which is a useful diagnostic for multi-party entanglement in quantum systems. Hopefully we've convinced you of that. And to compute binding complexity, or more generally complexity, we use the Euler-Arnold equation applied to the Nielsen framework. And then we studied the bulk expectations and computed the binding complexity and entropy of some states using Euclidean harmonic oscillator path integrals. And we found this very special class of graphs we called bipartite entanglement graphs, which reproduce several intuitions from holography, including the asymptotic scaling of the interior volume of the wormhole, as well as the Ryuta-Yanagi equation. So it would be very interesting, again, to compute this quantity, binding complexity, in a real holographic system to see if we could obtain a more precise matching. And finally, complexity perturbation theory results are matching quantitatively, at least, with the CFT single trace deformation story for creating a vacuum that supports a bulk wormhole. So thank you.
Any more questions? Also from people online, perhaps, if anyone has a question.
So I have like a basic question actually online. Can you explain like briefly once again like what was the deal with the Euler-Arnold equation? I mean like why it was so useful for you and how you arrived at it?
Maybe this one. Yeah.
Yeah.
Yeah. So the Euler-Arnold equation is whenever suppose you have some Lie group, right? This has the structure of a manifold, and you have a right invariant metric on it, which is exactly the case when we want to compute complexity. The Euler-Arnold equation is a very simplified version of the geodesic equation on such manifolds. And in fact, if you go back and read Nielsen's original papers on the reduction of this sort of complexity to circuit complexity, he actually suggests in those papers that the Euler-Arnold equation might be a valuable tool in computing this type of complexity. So that was the original motivation for us to consider this.
I think partly it simplifies the technical calculation in that you don't really have to find any explicit parameterization for the geodesic. You just solve this first order equation. It's very easy to impose symmetry conditions as constraints on the velocities of the path preparing the unitary. Yeah, I think overall it ends up being just technically easier to solve.
Yeah, you'll also notice that the Euler-Arnold equation, or the result of the Euler-Arnold equation, is completely coordinate free. So all it requires is a choice of basis of the Lie algebra, but we don't actually ever have to choose a set of coordinates on the manifold itself, which is very valuable. It simplifies the analysis quite a bit.
And how your results are sensitive to the choice of the right invariant metric, because that's not unique, right?
Good. So generally when one computes complexity, we're always talking about with respect to a particular gate set. So if you change this right invariant metric, what that corresponds to is you're changing the gate set. So there are some constraints on what you should pick for the right invariant metric that Nielsen talked about in the original papers on this subject. there are some, those translate into some constraints on the cost factors. But generally, when one computes complexity, we're not interested in things like overall constants or, you know, if a term in the metric is 1 or 2, it's not so important generally. The scaling is really what's important.
All right, thanks. I will look into the paper.
Any last questions from anyone? In that case, let's thank the speakers again.